Okay, so the brown triangles, one of the vertices is a family of Poncelet triangles interscribed between a circle and some generic caustic. Okay, and I can basically pick a different caustic here by just moving its foci. And whatever these foci are placed, I have a Ponceletian family here about that caustic. Okay, now what you see on the right, okay, is the brown triangle projected under this 3 by 3 matrix. Okay, so you get this green triangle, so a vertex corresponding to this A prime vertex. Now in both cases, I'm actually showing the locus of the barycenter, x2 of this family, over the motion, right? So this problem here has been studied, and it turns out that for a triangle family inscribed in a circle, regardless of the caustic, the locus of the barycenter is always a circle. Now here's what's happening on the other side. As I project the brown triangle to A prime, I'm also showing the locus of its barycenter, x2 prime. Okay, so it's that magenta ellipse. Now we know that for any Ponceletian family, the locus of certain triangle centers that are fixed linear combinations between x2 and x3 are always guaranteed to be conics. Okay, so this is a guaranteed conic, as would be x3, the locus of x3, the circumcenter, and the locus of x4, and so forth. Okay, but let's actually focus right now on the locus of the barycenter of the green triangle. Now here's the interesting generalization. No matter where my caustic is of the base system, if you follow these three numbers here on the left, you're going to see that the aspect ratio of the pink locus is maintained, as is the orientation of its axis. Here you're going to see some 180-degree jumps, but you can see here that the orientation and the eccentricity of the locus of the barycenter does not depend on the caustic. This is kind of remarkable, right? Given that the barycenter is not equivariant under full-on projectivities. It is equivariant if I had a simple affinity, making those bottom terms there 0. Okay, so now the barycenter is equivariant, but you get the same phenomenon here and for general projectivity. Okay, so before we had been rotating the caustic, we had been moving the caustic in and out, but now we can see that this is actually a more general phenomenon than we thought. Okay, now let's look at what happens to x3. x3 has no conservations for generic motions of the caustic, and even if this thing is an affinity, we don't conserve anything. Okay, so x3 is not our friend here. But how about x4? Under an affinity, x4, just like x2, conserves both eccentricity and orientation, and even under a full projectivity, those bottom terms different than 0, you can see here that x4, looking at the numbers on the left, conserves both eccentricity and axis orientation. Okay, so this is kind of remarkable, right? Because now we generalize this to any caustic. Any caustic, you get this really strange phenomenon here. Okay, now I'm just gonna do a preview here of what I'm thinking, especially if you go back to the x2 case. Okay, now how might this thing generalize to Poncelet's? I'm changing the projectivity here to be able to flesh out a bit this x2 locus here. Let's make it be a bit more, palatable like that. So how might this thing generalize to Ponceletian families where n equals greater than 3? Well, there's one triangle center or center of a polygon that you can compute, and that's the center of area of a polygon, the average of its vertices. So I'm starting to have a hunch here that when we generalize the system to n equals 4, n equals 5, we're going to see similar phenomena here. Namely that if I have an n greater than 3 Poncelet family interscribed between a circle and some generic caustic, or maybe a circular caustic in a bicentric case, there's going to be invariance on the locus of its barycenter and average of vertices, so center of variant, center of average of vertices over different families of caustics, perhaps an even generic one. So I'm constructing that simulation now. All right, see you on the next video.